Hi there, folks. Today we're looking at systems of equations in 3 variables. And this has a lot of similarities to what we did previously with 2 equations and 2 variables. The difference is we have to do more of the same stuff, all right? And so if you recall, the solution to a system of equations is that one ordered pair that's true for all of the things, all of the equations in the system, all right? And so that's what we're typically looking for. With a system of 3 equations, instead of an ordered pair, we're looking for an ordered triple, all right? And an ordered triple is kind of graphed in 3 dimensions. And that's really hard to express on a piece of paper like this. And we could do a whole unit on trying to graph these things, but it doesn't translate well when we're trying to do it on paper. For example, if I were to draw like a quick XY coordinate plane over here, so here's my y-axis, here's my x-axis. If you were to think about kind of plotting something on this axis, maybe I plotted a point go this way and up here and plotted it there. Now imagine that I added one more dimension, in other words, one more place to move. See, in this example, I moved to the right and I moved up, but now I have to move in a third direction. Imagine where that point is, picking your pencil up off the paper and lifting it into the air. And now think about the tip of that pencil. That represents that third dimension, kind of moving up off the paper. And so think about where the tip of that pencil is. That is a point kind of floating out in space. That's what we're talking about with an ordered triple. Okay, so on a piece of paper, x moves us left and right, y moves us up and down on the piece of paper, and then z lifts us off of the paper, and now we have a point floating out in space. Okay? And so an ordered triple is expressing that in terms of a graph. We're going to find it algebraically. All right. So if I were to look at something like this guy, I want to know, is this guy a solution to the system? And the only way to know if something is a solution to the system is to plug it in to all 3 equations and see if it works. So I'm going to plug it into this first guy. And again, the ordered triple is x, y, and then z. And I'm just going to simplify and see if this works. So let's see, that's a negative 10 plus 3 plus 8. That's a negative 7 plus 8. So I get a positive 1. And so this one works. Let me put a little check mark there. So then I ask the question again, is this a solution to the system? And the answer is, I don't know yet. Yeah, it worked for one, but it has to work for all of them. And there's really no way around it. I have to keep plugging this thing in. So I have to plug it into the next one. So let me plug it into the next one. Ready? So once again, I plug the negative 2 in for x. I plug the 1 in for y. And I plug the 4 in for z. And now I simplify. If you combine the negative 4 and the 4, they cancel out. So I'm just left with negative 1 essentially. And so I get negative 1 equals negative 1. Once again, that works. I put a little check mark and I say, okay, is this a solution to the system? Well, I still don't know because I have to plug it into that third one. Okay? Remember, it has to work for all of the equations in the system. It can't just work for one of them. It can't just work for 2 of them. So now I'm going to plug it into the third one and see if it works. Ready? So once again, I plug the negative 2 in for x. I plug the 1 in for y. And I plug the 4 in for z. And I simplify, ready? That's a positive 4 plus 2 minus 4. When I add that all up, I get a 2. And so when I look at this guy, that's ridiculous. That doesn't work at all. 2 does not equal the 3. So it worked for 2 out of 3. So the question is this a solution to the system? Well, the answer is no. All right, this one does not work. It's not a solution to the system because it didn't work for all 3. Okay? If I look at something like this guy, now we're going to solve this using algebraic methods. If I'm solving using algebraic methods, it's the same stuff that we've been doing. It's substitution and elimination. And notice, we skipped over one of our methods. We skipped over graphing because, once again, it doesn't translate well. It doesn't work well on paper. So if I were looking at this saying, okay, I'm going to use substitution or elimination, the reason I didn't give you any directions here on this one is because this one should be obvious. As you look at this, look at the 3 equations, you should notice something right away. You should look at this third equation and go, hey, I pretty much have x. I just have to add the 3 to each side. And once I add that 3, I get x equals 3. So now I know what x is. Well, it should be pretty easy to jump up to one of these other guys like this guy and say, well, let me plug in the x and see if I can find y. So here I plug the x value in. And now I can solve for y. So I simplify just a little bit. I combine like terms. I'm going to subtract that 25 from each side. And then I'm going to divide. Oh, sorry, this was clearly a 5 that I wrote down incorrectly. Must be glancing around too quick. Gonna have to get. So I end up with y equals a positive 5. I'm still not done though. I got to plug it into the next one. And notice this is pretty similar to doing a system of equations by substitution like we normally would, but I've had to do substitution a little bit more than I normally would have. So here I plug the 3 in. I also know y, that's the 5. And now I can solve this thing for z. All right, so here, let's see, that's 3 minus 15. Once again, I combine like terms. Sorry, I missed my plus sign here. So that gives me a negative 8. And I'm going to add the 8 to each side. And divide by that negative 2. So I end up with z equals a negative 4. And once again, I write my order kind of like I did before. I used to write them as ordered pairs. Now I'm going to write it as an ordered triple. I've got 3, 5, and negative 4. And I write it in this format. That's a nice, succinct way of saying, hey, x equals this, y equals this, z equals this. Okay? If I look at the next one, these are going to get more complicated. So what we want to do here is we want to create a system of 2 equations. Okay, so I'm going to create a system of 2 equations, and I'm going to do that through substitution or elimination. It's a little bit more difficult when it's like the previous example. I pretty much had x right away, and that was all I needed, right, to get everything else. Now that's not going to be the case. I have to work a little bit harder. And the key here is to make sure that you do each of these things twice. So substitution, I isolate a variable, and then I substitute it into each of the other equations. So that's going to be substitution twice. See, I used to isolate a variable and substitute it into the other equation. Now it's isolate a variable and substitute it into each of the other equations. All right? And the net result of that is not going to give me one of the variables. The net result of that is going to give me a system of 2 equations with 2 variables. So then I hit the reset button and solve it the way I've always solved those. Okay? Elimination. Elimination, I take the same approach. I eliminate one of the variables. So I eliminate using 2 of the equations. I eliminate one of the variables. But then the problem is that I've used 2 equations, but not the third one. So now I have to eliminate again, just like I had to substitute again. I have to eliminate again, and I have to use that third equation. All right? And again, the net result is not going to give me a value for any of the variables. It's going to give me a system of 2 equations and 2 variables, which I have to solve by my previous methods. Okay? So let's take a look at an example. All right, so if I take a look at this guy, again, I'm going to do substitution, then we're going to do the same example using elimination. So if I wanted to do substitution for this one, I have to isolate one of the variables. And if you look, that third equation is probably the easiest place to isolate. So you can isolate x, y, or z. Any one of them would work. Let's eliminate, get x by itself. So I'm going to subtract the y and the z from each side. And so the result is this. It's x equals negative y minus z. Okay? And so now what I want to do is I want to substitute that in. But unlike before, it's not just one equation I have to substitute into. It's 2 of them. So I have to substitute this in twice. Okay? So I'm going to substitute it into this guy. I'm going to replace the x with the negative y minus z. And now I can simplify. So here it's my distributive property. And then combine like terms. And that's all I can do with this equation. You're probably looking at it going, well, that didn't help, Mr. Jansen. Well, it did. You just don't realize that it did yet, okay? See, the difference here is, yeah, it didn't solve for one of the variables, but what it did is it gave me an equation with less variables. See, my original equation that I started with had 3 variables, x, y, and z, but the equation I ended with only has 2 variables, y and z. There's no x, okay? And so now I have to continue the process. I have to substitute again. Let me do this other equation. And I have to do it in here. Ready? If I substitute into that one, again, I'm replacing x with that negative y minus z. I have to do the substitution twice. That's what makes this thing work, is doing that same thing that we've done, but doing it multiple times within the same problem. And now once again, I'm gonna simplify. I'm gonna distribute. Combine like terms. Oh boy, that's a lot of 7s. And once again, at first glance, you might say, well, this didn't help, Mr. Jansen. All right, I still have variables, but the point is I have less variables. See, and if I kind of just hit the reset button here, if I go, hey, let's take a time out. Let me write down the 2 equations that we just came up with. The first one was a negative 5y minus 3z equals a negative 21. And the second equation that I came up with here is a negative 7y plus 7z equals a negative 7. All right, so now let's all of a sudden pretend that I haven't done any of the things that I've done so far. Let's pretend for a second that I'm starting a new problem. Okay, that's kind of how you have to approach this. You know, we ignore everything that we've done and we say, hey, let's take a look at this thing right here and let's just solve this system of equations. If this was the problem that you were given, how do we solve it? Okay? And so this is just a system of 2 equations, 2 variables. You can solve it by substitution or elimination. It doesn't matter that we started this thing a while ago using substitution. We can keep using that, or we can switch to elimination now. We're hitting the reset button here. We're starting over. This is now a new problem. It's a system of 2 equations, 2 variables. We know how to solve that. All right? Me personally, I think that substitution is actually the easiest version for this one, but I think most students would look at this and say, hey, let's do elimination. So I'm going to do elimination because I think that's what most students would do here. All right? So for this one, I would probably try to eliminate z. So to eliminate z for this one, I have to multiply this first equation, looks like by a 7. And I have to multiply the second equation by a 3. Okay? So now let me write this new set of equations here. Let's see, I've got a negative 35 y minus 21z equals, I believe that's a negative 147. And then down here, that's a negative 21y plus 21z equals a negative 21, okay? And see, what I'm doing here is I'm going to eliminate those z values. So now I can add these guys up. So here I add it up and I get a negative, looks like 56y. The z's cancel out. Over here it looks like I get a negative 168. And now I can solve this thing by dividing each side. So I divide each side by that negative 56. So I end up with y equals a 3. See, now I've finally gotten to solve for one of my variables. And, you know, that's what happens when we do substitution or elimination with a system of 2 equations and 2 variables. The net result is I get one of the variables. I get to see what one of those things is. All right? And that's the thing that is kind of not comforting to us when we do a system of 3 equations. We got down to 2 variables and 2 equations. Now we're back to doing what we normally do. And so now from here, I have to plug this back in and find that z value. You can pick either one of these. I'm just going to use the first equation, negative 5y minus 3 times z, which is the y is the 3. Let me try again. And now I can solve this for z. I don't like the way that looks. And so now from here, that's a negative 15 minus 3z equals a negative 21. I'm going to add that 15 to each side. So that's a negative 3z equals a negative 6. And now divide each side. And so the result here is I solved the system of two equations and two variables. I took this problem, all right, this new problem that I created, and I solved for y and z. But now that I've done that, I can't keep ignoring all that stuff I did earlier. It's hiding up there. I have to kind of scroll back up and look at this. Ready? Let's go back up there and see what it looked like. See, I did all this stuff before. There's still one more variable. It's that x value. And so right here, if I scroll down just a little bit, let me bring this guy down. I can now find the x value. X equals a negative y, which we know to be a 3, minus z, which is a 2. So I get x equals a negative 5. Okay? When I solve a system of three equations and three variables, I do a substitution twice to get a system of two equations and two variables. Then I solve that system of equations. And when I'm done with that, I can go back to find the third variable. All right? Let me show you, well, first let's write this as an ordered triple, our good buddy ordered triple. And now we'll go and do this thing by elimination. All right? So that was substitution. I isolated one of them, and then I substituted twice. For elimination, I have to do elimination twice, all right? So I have to choose to eliminate one of these variables. And most of the time, students are going to look at this and say, hey, check out these second two equations. If I look at those second two equations, let me rewrite them up here. They're really easy to eliminate z. So students will take these second two equations and go, all right, let me eliminate z. Because it's already set up nicely for eliminating z, I add them up. Let's see, I get a 3x minus 2y. The z's cancel out, equals a negative 21. Fantastic. But notice, once again, it didn't solve for one of my variables. It just got rid of one of the variables, so I have an equation with less variables. But now I have to do elimination again, and I have to eliminate the same thing. I have to eliminate z again. And the other rule here, and this is what is a little bit tricky with elimination, is I have to use the equation I haven't used yet. Notice, I added these two equations together. I used the second two equations. I have to eliminate z again, and I have to use the 3x minus 4y plus 10z. And I think the thing that bothers students there is that's not the easiest equation to eliminate z from, all right? But I have to use that one. And now from here, I can use either one of the other two. So maybe I'll take that third equation and I'll multiply it by something like a negative 10. And yeah, I could have used the middle equation multiplied by 10, but then I'm dealing with larger values. Try to make it as easy as possible. So here I would get a negative 10x minus 10y. If I could write, I would write a y instead of an x like a crazy person, minus 10z equals 0. And now I add these up. So once again, I am just eliminating a second time. So here I get a negative 7x. Here I get a negative 14y. The z's cancel out, and here I get a negative 7. And now once again, I haven't solved for any of the variables. I've simply created two equations that only have x and y and don't have any z's. I've created a system of two equations and two variables, if I read those off to the side here. Okay? And so what I do is I hit the reset button. I say, you know what? Time out. Let's go back to what we already know how to do, systems of two equations and two variables, and let's solve this thing. Ignore everything else that I've done. Let's solve. And I want to solve this one by either substitution or elimination. You can choose either one here. I think most students, once again, would go with elimination for this one. I think substitution, once again, is easier, but that's okay. I'm going to multiply this first equation. Let's eliminate y. I'm going to multiply that first equation by a negative 7. Okay? And so once again, let me write this off to the side. So let's see. That's a negative 21 plus 14y equals, this should look familiar. That was a 147, I believe. And then here, that's a negative 7. Sorry, I didn't write my x up here. Negative 7x minus 14y equals a negative 7. And now I can add them up. I'm going to eliminate y. And yeah, the numbers are large, but it's not anything different than what we're used to. It's a negative 28x. The y's cancel. And over here, I get a 140. And now from here, I can finish solving. I'm going to divide each side by a negative 28. So I get x equals a negative 5. I'm not done with this new system of equations. I have to plug it back in. So I'd probably pick that first equation, 3x minus 2y equals a negative 21. And now I solve. Doing my simplification. And this should look familiar. This is, when we get down to this system of two equations, two variables, we might see things that look familiar. It's the same numbers or the same values, or maybe even the same equations for some of these. And that will happen, okay? So here I get a negative 6, and I divide. And so once again, we've kind of been ignoring everything we did to start, and I've solved this new system of equations, but now I have to go back and say, wait a minute, this was part of a bigger system. Remember, I had 3 equations and 3 variables before. Maybe we take this third one and say, you know what? X is a negative 5, plus y is a positive 3, plus z equals 0. And now let's finish solving for z. Okay? And I add that 2. So I end up with z equals a positive 2. All right? And once again, I'm going to write my answer as an ordered triple here. Let's see, it was negative 5, comma, 3, comma, 2. And again, this was the same one. I was just doing it by elimination this time. Let's double check to make sure we got the same answer each time. Negative 5, 3, 2, negative 5, 3, 2. Okay? So again, the idea here is you have to, if you do substitution, you have to do it twice. You isolate and substitute it into both other equations. That creates a system of two equations, two variables. Hit the reset button. For elimination, you eliminate one of the variables, but then you have to do it again using the third equation. So you eliminate twice, which creates a system of two equations, two variables, and then you hit the reset button. Okay?